Thank you so much, Catherine. My name is Professor Virginia Kilborn, and I'm the Chief Scientist here at Swinburne University of Technology. It's my great pleasure to be working across many different areas of science here at Swinburne, including medical technologies, space and astronomy, and of course this innovative planet topic, which is so important for us, as we've just heard. It's my great pleasure this morning to be introducing our keynote speakers. And I'm sure we're going to learn a lot from their knowledge, and I'm really glad to have them with us today. So first of all, we'll have Dr. Gilbert Brunet talking about accelerating the global climate R&D effort. Dr. Gilbert Brunet obtained his PhD in meteorology at Ecole University in 1989. He was director of the Meteorological Research Division for 2006 to 2018 for Environment Canada, including a secondment as Director of Weather Science at the Met Office in the United Kingdom. He was previously head and research scientist at the Numerical Prediction Research section of MRD. In the last 2 decades, he's developed a strategic vision of the way forward for complex multidisciplinary science of the Earth system prediction. His leadership was recognised by his nomination as chair of the scientific committee of the WWRP for the World Meteorological Organization. And in that role, he's contributed to several international significant strategic planning activities in weather and climate science, and contributed to the way forward for scientific challenges of prediction from weeks to decades. From a scientific research perspective, he's recognised as an expert in weather and climate dynamics. His work covers analytical and empirical studies of wave processes from regional to planetary scale, and numerical weather prediction from minutes to seasons. Welcome, Dr. Brunet. Thank you.
Thank you very much for the introduction. And thank you for AFRAN to invite me to speak to you this morning about something which I think is very important. And I would like to do an approach. I know you're not all expert in what I would call Earth system prediction or simulation. So what I'll do, I'll explain you the important aspect of this science by doing sort of historical survey, where this is coming from. And you'll see this is a science which is based a lot on technology. So happy to be here, University of Swinburne Technology, because it is a science which is driven by technology. With no technology, this will not go anywhere. And I'll say around this journey, the next few slides, I will also point out contribution from France and Australia, and by the way, from some French Canadian also. And next slide, I think I can do this here. Yes. Right. So what we get here, do you have the laser with this? Can we use the laser also? Yes, great. So it started, and I need to stay in front of the microphone. Yes, I agree. So it started, it's okay, I have a laser here. Oh, no microphone, right? Okay. So first, to start doing a prediction and for climate or weather timescale, you need to have observation. And France, Australia started a long time ago this type of measurement. Philippe Leher in Paris started in the 17th century, and in Australia more recently, Clark Ross and Charles Todd in Adelaide done that starting in 1855. So this is the first ingredient, and this will come back all along our discussion, observation. Something which maybe less known is that Robert Fitzroy, which is known really well in Australia, which was the captain of the HMS Beagle, founded the first meteorological service in UK in 1854. Why? Because we had those observations, but to do a prediction, you need to bring to all the same place the observation quickly so you can make a prediction. And the telegraph was the second technology to be able to make this happen. Telecommunication is an important ingredient of that science. And so they had the first public forecast appeared in the Times on the 1st August, 1861. It didn't work so well sometimes. He was blamed for a lot of things. Fitzroy about the forecast was missed. And I can tell you, this is really what I'm living also. I've always been said, we need to do better. And I'm fine, because this is why I'm having a job today, is because I need to improve those forecasts. But I'll say a few words on that later. So be patient. That's the only mathematics I'll show you today. But I just want to insist on the point that numerical weather prediction and climate simulation are based on a law of physics of a fluid on a rotating planet. So it's really an initial value problem of fluid mechanics. And this was realized by two persons, the American Abbey and the Norwegian Berknes. And this was done at the beginning of the century, last century. And they didn't know how to resolve those equations. They are complex, they are nonlinear. You cannot find exact solution by hand, but with analytical techniques. So they decided to stop. This was two nice papers. They're well known for that. But you had to do the next step. The next step was done by, first, before we go to the next step, how to solve the equation, one person, they realized also it was a very difficult problem to do. And it's a well-known person, Henri Poincaré, where he was working on the three-body problem, a celestial problem. And he realized that if you just do a little change in the initial condition of the trajectory, it will this area will exponentially grow in the time. And this is the characteristic of a chaotic system. And it explains why it's so difficult to do numerical prediction of weather in the next few days, weeks, and also to do climate simulation in part. And he was the first one to realize that a small error in the former will produce enormous error in later. The meteorologists see very well that the equilibrium is unstable, that the cyclone will be formed somewhere, but exactly where they are not in a position to say, 1/10 of a degree, more or less at any given point, and the cyclone will burst here and not there. And so that was a very nice way of saying this problem is a chaotic system, and we'll need to actualize also the techniques to deal with it. First one to have a try at solving those equations is the British Richardson physicist. And essentially, he realized we could do an approximation of those equations and to discretize them using sophisticated mathematical algorithm and calculation techniques. And this was around 1922, after the First World War. And in this book on this, he decided, okay, how I make this computation. So he designed this spherical room, very large spherical room with galleries of people. Each people, he called them people were computing. And it was only at the time for banking and all that you use people called computers, and they do that sort of calculation. So to make a prediction of good quality for the next 1-2 days, he realized he would need 64,000 people in that building to make it happen. So of course, he went and started doing other things because this was not possible to do. But anyone who are now familiar with supercomputers, massively parallel supercomputers, well, that was the first depiction of a supercomputer. And you'll see that all the science of weather and climate prediction and simulation is based on those supercomputers to resolve those equations I've shown you just before. The first one really to do that was after the Second World War. They were developing computers that you could code. They were generic computers. You could code them to do whatever you want to achieve. It was done also in Australia at CSIROC here in Melbourne. If you walk on the campus of University of Melbourne, you'll find a place where there's a plate on the wall. This was the place where the first computer in Australia was operated. And this was done by Percy. And von Neumann, pioneer of modern computers, decided to work with Charney, the meteorologist, an American, to do their first forecast. They all knew the problem with Richardson. They really knew this could be possible if we had a computer. It was a well-known problem. Maybe I should add also Poincaré was the PhD supervisor of NetNet, the one who wrote those equations. So they all knew this, but it was in the community. They knew this was a problem to crack. So the first computer was used to do this prediction with success, in fact. And from there, it started. And I'll show you a little bit how much progress we have done since then in the 50s. But I would like to bring a point here important because it's part of my story here. Charney's thinking on weather and climate prediction was visionary, clearly. He first decided we need to do an international collaboration to try to advance that science. This is a too big problem just for the US or France, or whatever. You need to work together. And he created this CalCARP, Global Atmospheric Research Program, which was the first international collaboration to improve those systems. And he was very ambitious because he said, we'll do first the weather prediction problem, and we'll do that in 10 years. Well, we're still working on that now. But he said, after 10 years, I'll take an even more important problem. I'll do simulation with the same system, and I'll do the carbon dioxide and climate problem. And since I'm using this model to do weather prediction, I'll be able to say, yes, the planet is getting more warm. This was new already by some research in 19th century. Arrhenius shown that most carbon dioxide would mean the planet is getting warmer. But Charney want to see, okay, and what is the impact on tropical cyclone? What will be the same impact on the weather regionally? First, he said we need to do a model who is able to predict weather, and then I'll use it to do climate simulation. Well, we could not do that. And I would say in around the 60s, essentially the climate community went in a direction and the weather communication went in another direction, and using the supercomputers, but not able to do the same at the same time. What I want to argue today is that we are there now. We are able to do the weather characteristics, the statistics in the climate simulation. And I'll tell you what we need to do to achieve this. So 60s, like to add that we had first developed the Canadian in Montreal. So why someone like me here, which made this speech in Montreal, talk about this problem, because Henri Robert, which is a French Canadian, developed the first global model. Before, our model was regional, and you cannot do climate simulation with a regional model. You need to be global, and you need to take account of everything. And this was done in collaboration with someone from the Bureau of Meteorology, Bill Buche, the Australian. So this was a collaboration there a long time ago. And this is now the ancestor of all existing global spectral weather and climate computer models, like the one used at the European Center. Also in the 60s, more and more observation. Observation is coming back now. We have supercomputers, we have observation, telecommunication, and observation just started to build up more and more from space, which was very, very important for what we try to achieve. What can you say about the supercomputers? Let's go back in the 70s at the European Center. European Center, which is centers which have been developed by the European community, where I would say in great part, Météo France and the Met Office contribute a lot. In fact, the director of the European Centers now is Florence Raby, which is an engineer from the School of Météo France in Toulouse. So the France have contributed a lot to this problem. So you can see here from 1979 to 2023, and this is this capability of the computer, how powerful it is. And you see this line, it's a logarithmic graph, so it's a line of increasing power of supercomputer along the years. And just here we depict a tropical cyclone at those resolution, at 120 kilometer resolution, then 64, 40, 16, 9 kilometer. It's getting more realistic, but not just the look, but also the intensity, the tracking in terms of prediction is improving a lot with the more supercomputer power. We think in the next 10, 15 years, we'll be able to achieve kilometer resolution globally, not only for predicting, but also to do climate simulation, which bring together now weather and climate simulation. And we are at a very important point here in terms of science. So enough of this, I just want to do a quiz with you. There's one here of this planet with clouds on it, which is observation. And the other one is a 3-5 day forecast from the European Center. So I would like you to tell me which one is a reality and which one is a simulation. And this is done at 10-kilometer resolution. That's probably what you have now in terms of global prediction for your weather each day. So anyone is courageous enough to try? Okay. So, well, why? Okay. No, okay, yes, well, you got it there first. Yeah, sorry. I just pushing too much with button. So the observation for Meteosat is there on the left, and this is the European Center forecast on the right. Note that there's some information in the one which is observation, but you need to realize the right one include almost 40 million new observation each day to do this forecast, which is a lot more than what is the truth on the left. We integrate all the observation of the world at the same time, planes going up, going down, ships on the ocean, and those models now are coupled to the ocean, so they're getting more like an Earth system prediction. We're predicting the ocean at the same time, the land surface, and the water cycle. And we think that the water cycle will be very well done for global simulation, climate or prediction, when it will be at the kilometer resolution. And that's the point where we are now, is that we have those systems which are used for all sorts of application. And we have for different time scale, lead time, projection, climate change, climate variability, weather, to make also the decision-making, early warnings, sectoral preparedness planning, inventory, eventually international policy negotiation. And that's the quality of the prediction we can do with some uncertainties, very important. Part of that uncertainty in the short term here is linked to what Poincaré was talking about. This is a chaotic system. And we make decisions based on this more and more with those Earth system models. And paper just came out in Nature Climate Change a few months ago. I think that's where the dream of Charney's is coming, is to put the weather in those climate simulation. But this would mean, like I've shown you, supercomputers that we'll get in 10 years, 15 years from now. But if you put $1 billion on the table, you can have them now, okay? So they are existing, but never used to do that sort of simulation. So the push is to try to have a place where we could start doing those experiment simulation. Very important for all sort of reasons. I'll give you an example just in a few slides. And so the World Meteorological Organization, which is a United Nations agency, a scientific one, of course, has decided for the next to 24, 27 for the strategy, different long-term goal. One is advanced targeted research. WMO is very well known for sharing observation all around the world, and have done that very well for 50 years. But now they want to coordinate more research, but they feel we could accelerate information which is actionable to make decision. Okay, I'll give you an example in a few slides. So, as I'm chair also the science advisory panel for WMO for the last 2-3 years. And one thing we've been asked to develop this vision for the next 10 years. And we have developed this World Meteorological Organization Science and Technology vision. And I won't dwell too much on this since I'm sure time is running, but I'll give you an example why this is pressing and demanded. Recently, as you probably know, there was a COP conference in Egypt. And increasing demand for climate service was clearly stated at this meeting. It's a political hot potato. The in and out of mitigation, adaptation, finance are also still hotly disputed. Loss and damage were doing the first page along this meeting. And one thing which is difficult, they're not able to quantify the attribution, so you can decide who should get the compensation and all this. So we need to bring this information. And essentially it's saying, what's happening with the weather? Can I attribute this type of weather, neutral, more intense tropical cycle? What we got for the last 3 years here, wet Melbourne, is it attributable? Can we attribute this to climate change? regionally, that's what we need to have more information. It's very important to quantify. So to resolve it, they're asking the IPCC to bring more forward the science there. But the science is still not there. We need to do those very high simulation, climate simulation. And I would refer you to the paper Nature I just mentioned before, so to see exactly why. Recommendation of this vision that we have developed with the international community is the first one: major international climate R&D effort and exploitation of global came in kilometer scale, K-scale computing and Earth system observation. And also we need to have better observation to make this happen. So that will be a push. Also, the second is very important. Also, the second recommendation. There's 8 of them. I won't go to all of them, just those first two. But this one is about helping also to bridge the gap between developing global science and delivering local impact, especially for low-income countries. And to do this, we believe, and that's another paper which I've contributed to, is to do this research development, put in operation, service, all of this called the innovation cycle and that science. We need really to get engaged with the public sector also, not only the public, but the private sector. It's very important to work with them. And let's see, for the second recommendation, people think more and more that we could have on the cloud those global prediction, but countries which are low income cannot support infrastructure supercomputing could download the tools and use them in the cloud and be able to do downscaling for their own region, have more information relevant to what they are. So that's another push we're doing to make sure that those people can access more information. Also, I would say 40 years ago, computers were operated by the Met Service. They're not anymore, more or less. More and more this is provided to the cloud, but it's provided by cloud industry. I'll give you an example. The Met Office just signed a £1 billion contract with Microsoft for the next 10 years to have the supercomputer in the cloud on Azure. Because for all sort of reasons, first, the customer, the people are in the cloud now, so you need to be there also. And those machines, those computers are getting so complex that a Met Service by itself has a lot of difficulty to maintain that. And I can talk for the Bureau, it's getting really complex to deal with this. So we're thinking more and more to use the cloud also and provide to do our calculation, our research. If you do that also, and I'll finish on this, it's very important because if you collaborate with the Met Office, with the US or for France, through the cloud, using the same tool and all this, it's really more efficient. We think this will be a revolution also for research collaboration, not only in our field, but in other fields also. So that's something we want to go in the future. And that's it. Thank you. Merci. Quite keen to get some question if I have time or not. Okay, after. Okay, great.
Thank you so much, Dr. Brunet. That was a wonderful talk, and I think we have really understood that importance of really those detailed mathematical underpinnings of the modelling combined with the supercomputing power that we need to make these observations, plus that worldwide collaboration that we're going to need to go forward in this field. So thank you so much for your insights this morning. It's now my pleasure to welcome the second speaker for this morning, Professor Cédric Buche. Professor Buche is a professor at the National Engineering School of Brest in France, an adjunct professor at the University of Adelaide and at Flinders University. He is also part of the CNRS International Research Laboratory crossing team since 2021. His research activities are in artificial intelligence, virtual reality, machine learning, robotics, video games, and human factors. His interest is to transfer his algorithms to concrete solutions. As a result, he's participated in different competitions and has won the Robo Cup at Home 2022 competition in this year. In 2022, he received the Trophy of French of the Year in Australia. Professor Buche will talk to us about human autonomous agents teaming. Welcome, Professor.
Thank you so much. I would like to thank the AFRAN for the invitation and also the embassy. It's so nice to be here, to be present in Montreal. So I will start to introduce myself. So I was a student in Brest at the National Engineering School a long time ago, as you can see. I start with experiences in US, especially in Hawaii, working on video games. And after that, I got a dual degree, engineering degree on what we call at DEA. If you are too young, you don't know what is it, but so it was a mandatory degree to go in a PhD program. So I got my PhD in virtual reality and artificial intelligence. And after that, I got an habilitation degree. This is something that you don't have in Australia. We have this in France and Germany, as I know. 2 years ago, I moved to Adelaide as a delegation for CNRS in the lab called Crossing. So my goal is to make some algorithm for decision making that can be for virtual humans or real robots. So as you know, this kind of entity are quite stupid right now. My goal is to make them a little bit better, maybe. On the tricky part is, I have a laser, maybe. This guy, on this guy. So in my algorithm, we consider that the virtual human or the robot are in interaction with the human. And this is very tricky because this guy can do what he wants. So you cannot predict anything. Okay. So to do that, to solve this problem, interaction with somebody that you cannot control, you have to adapt. And to do that, we use techniques that call learning by doing. That means the robot or the virtual human is learning while acting, while interacting. And to do that, we consider that the human will be very important. So we need to interact with the human, we need to observe the human, and we need to maybe to substitute to the human. So if you are aware of machine learning techniques, it's called interactive machine learning, human in the loop, reinforcement learning, stuff like that. So today I will focus my speech on human-robot interaction, not human virtual human interaction. So there is a famous competition, it's called RoboCup. I don't know if you are aware of this competition. So it's like the world one-chip competition. So there is 4,000 robots, 4,000 programmers, and a lot of people. So if you are, let's say in Japan or in Taiwan or stuff like that, it's on the TV, like TF1. Okay, so it's super famous. There is 5 leagues, 5 different competitions. We are part of 2. The first one is RoboCup Soccer. So this means we have some small robots like that, 60 centimeters, that play soccer. They are completely autonomous. So it's like the World Cup soccer right now. There is some qualification. After that, you go to a different round, quart final, semi-final, and so on. I think I have a video.
This is the grand final between Runswift in the blue and like Cedric hanging the grid.
Leaving the field! Nope! Leaving the field! Look. Leaving the field! Look, bye!
So as you can see, it's fun. It's 6 robots against 6 robots. They are completely autonomous. They have no connection with internet, no connection with nothing. It's exactly the same rules that humans. So I don't have the robot with me, but the robot is like that. And the robot is moving like that. On the camera, it's just here. So that means you have a very bad quality of images, and you need to deal with that. The robot is like your cell phone 10 years ago. The power is not good at all, and you have to manage that. So it's very interesting. And at Crossing, we are working on the goalkeeper. And to do that, we take inspiration from the human, as I explained before. So the technique I'm using is that the goalkeepers try to imagine what is going to happen using an internal simulation. This is what the human is doing. You simulate in your brain that, okay, I think the ball is going to be that way, so I'm going to do this motion. And if I do this motion, maybe I can stop the ball. So we are doing that here. So this is the main simulation where the robot is doing actions. And here you have multiple simulation in parallel when we try different solutions. Let's say I will move like that. Let's say I will move like that. Let's say I will move like that. What is going to happen? So it's like if the robot is simulate in its brain different options. When he finished to simulate the multiple simulation, he takes the best options and apply in the simulation. So this is what we call simulation in the simulation. Right now in artificial intelligence, some people are talking more about simulation, machine learning by imagination. So it's quite complex. It's simulation in simulation. If you have seen the movie Matrix, it's something like that. They simulate their brain that simulates something. So after this kind of simulation, you can learn your bot how to move, and you can try to apply in real. This is what I've done here. So you will see the results. So as you will see, when you move from simulation to real, what I've done is I play with my robot during 1 week. And the robot So yeah, as I said, it's super interesting. We have simulation in the simulation, which is like the human. And we have learning by interaction, interacting with the system learns from you. So it's far away from super calculator doing a lot of job during weeks and weeks. So the second application is Robocup at home. So it's completely different. You have a humanoid robot, this size, who is going to interact with the human. And this is the goal of the competition. So we have a team. in Brest, we call Robotics. And we take some very important consideration. So we decide not to have any connection with internet. So in this competition, you can have a connection with internet, but we decide it's not a good idea. I will explain why. Actually, we decide we have no connection with nothing. The robot is doing its job and that's it. So everything is on board and it's super complicated. We need to have algorithm on vision. So the robot need to detect object, human activities. The robot need to navigate. So you will see in the competition, there is like a fake apartment with 3 rooms, and the robot need to move from one room to another one. The robot need to interact with the human, and the robot need to do something which makes sense. Right? So we decide to have no connection because we think it's important to keep the privacy of people. So in the future, you will have robot at home for sure, but I'm not sure you are okay to have connection with Google. I'm not. I don't know about you, but I don't want to transmit my images on my son to Facebook or whatever. So we think it's super important. And it's also super important for environments because transmitting images, sound, and stuff like that for nothing, that doesn't make sense at all. So in this competition, there's 2 stages. The first stage is a qualification. So you need to send a video to an international committee. We decide if you are qualified or not. This is what we have done last week, and this is the result. We need to display everything that you can do. Like, immediately now you are going to see now nice very interesting. People which is very important. I study robotics, very important.
Could you please indicate your orders? Would you kindly speak as loud as possible?
Tell me what's the biggest object on the end table.
I want a new jacket.
The category of this question is statement, non-opinion. The main topic is a new jacket. The sentiment is mainly neutral. I view the user as materialistic. The user intents is to be warm. The user may wants to go to the store. I believe the user command is used for winter.
All right, so after qualification, last year we were qualified, you go to the competition. So it's a 1 week of competition. Every day you have tasks to do. There is like 40 robots in line outside of the fake apartment waiting for their turn. And when the jury asks you to come, the robot needs to enter in the room. This is what you can see here. Start. All start. Just the robot. All right, I have only 1 minute. So last year, sorry, was the first time we compete, and we are super happy to win. So that means the AFRAN Crossing is like world champion in social robotics. And we think it's a great achievement because it's a collaboration between France and Australia. We have students from France moving to Australia. We have Australian students in the lab. So we think it's super nice. Thank you so much.
Thank you so much for the wonderful talk. Don't go away too far because we're going to take questions from the audience, if that's okay. So really wonderful to see the work and to see your success in this area. And it's just amazing to me to see the advances in this field, especially the self-learning and the autonomous development of those robots. So congratulations. So we have 5 minutes for questions from the audience here and for those online. I think you can type them into the chat. So please, I'll open it up for questions. We'll just wait for if you can introduce yourself and reintroduce yourself and use the microphone. Thank you.
I'm not Boris Toukas. Yeah, Thierry Corrège, sorry. I have a question for you, Gilbert. You said that the next step is to have computers able to do kilometer resolution. Do you think we know enough about the physics that we have to put in the computers in the simulation, especially the physics of clouds and so on? So when you work in climate change, you always hear that we need to do more about this physics. So how are we today? Do you think we still have to improve, or we can already gain by just having a smaller mesh in the models?
Yeah, that's a very good question. I think there is still a lot of open questions, but let's hit the physics and the clouds and all this. At kilometer resolution, that goes back to this churning problem where you said, let's do the weather first, problem, predicting weather, and do the climate afterward. And then we realized we could not do that at the same time in the 60s, 70s. It went two ways. Weather prediction knows very well how to do at a kilometer scale, but they do it for a fixed small region. We have like over all the cities of Australia now, kilometer resolution model predicting rain, predicting storms and things like that, but not globally, okay? So the plan is to have the weather community working with the climate community, which is sort of new, okay? And to bring the science that weather has developed, weather prediction has developed in the last few decades, and to bring this in a global model and to go together. So there'll be, of course, little glitch question along the way, but we know quite well how to do kilometer resolution. Presently, the weather community is working better than that for Paris 2024. There is for the Olympics, there is a big experimental program to do sub-kilometer, okay, 100 meter, 50 meter resolution. That won't happen for climate simulation before the next 20 years, but the weather community is already looking into this. So the science is there, but there's a lot of open question. Let's say, how we close the water cycle, how we make sure all the water goes on the ground, goes on the river, the ocean, evaporate, all this closed properly. That's work we're doing presently at the Bureau. Chris is someone who's pushing this project. So there's still a lot of open question how we do those things. And especially for a global system, that will be very challenging. But yes, we know where to go. Yeah.
This is for Gilbert again. So my name is Romain Ragonnet. I work at Nationale University and I do epidemic modeling. So I believe our fields have a lot of similarities in the sense that we use complex mathematical models trying to simulate natural phenomena. One of the main issues we have, and I think you've covered it very well today, is about computer power, that we need more and more computational methods as the equations get more complex and things like that. Another thing I'd like to ask you is about uncertainty, because that's one major issue for mathematical modeling in general. What are the main sources of uncertainty for climate and weather forecast?
No, that's a very good question. I would say there's a first I would call the geophysical uncertainties, which goes back to Poincaré, okay, the chaotic system. So there's a lot of variability. You can have a phenomena like a drought will come back each 100 years, let's say, and the system you cannot predict very well because the system is chaotic. But it should come back each 100 years, the frequency. Now the question for climate change is, so let's say we have this uncertainty linked to the geophysical system. Now the question is, if I increase the greenhouse gases, how much this 100 years will change maybe to 10 years, okay? We'll have more recurrent drought. The uncertainty here is more, are we getting, it will be able to control the greenhouse gas emission? There's many scenarios. We have really pessimistic scenarios, the 2.5 Celsius. I can tell you those systems show that when you go to 3 Celsius global increase or 4, and then system bifurcate somewhere else, okay? Who will be in another planet, okay? But so we're not sure how quick we'll be able to react, to control, to mitigate those emissions. And that's another uncertainty. So the combination of the two is all what we need to understand in this simulation. And I think that the one link to the society is more difficult, of course, because we don't know what happened. We can see a change in politics in some country and suddenly nothing is happening, and change of politics and everyone's starting to work on it. So that's really a question mark.
Hello, I'm Jean-Philippe Diguet, the director of ERL Crossing, the CNRS lab in Adelaide, where Cedric is in. So this is where Cedric is doing his research on AI and robots. And I've seen a paradox between your two presentations. So in your case, your need, I was very happy to see how much important were the processors and the computers, or the progress in computers to get your estimation, to allow the computation of your very complicated models. So you need computers, you need the cloud, you need a lot of power to make these estimations. In the case of Cedric, he tried to use the small resources which are available in small robots to implement very complicated AI. So my question is, as you know, computers and networks is accounting now for about 20% of electricity in the world. So it contributes to the climate change as well. But for you, it's necessary for your computation. So how do you think it's a kind of necessary level, or
That's a very, I see
or how do you deal with that?
It's a very good question. In fact, it is. Now we realize we can develop algorithms for those Earth simulation that could be more energy efficient to start with. In fact, it brings a little bit of noise, which sometimes it's good to bring noise in the system because there's a lot of things we don't know. And so there's a lot of ideas there like that. And we could make them more efficient. Machine learning, AI, is used now in the system to emulate some of the physical process in a really more better way, in an energy efficient way to do it. So this time are getting more energy efficient. And some people suggest that, let's say in Australia, what we call those exascale type of supercomputer, they need to have a target zero. This is the 8th recommendation in our report, but I didn't talk about it. We need to be having a net zero target. And Australia could be a great place for that, because you could have a supercomputer with solar energy. You would achieve something which has a net zero contribution. And that's part of it. I don't know how they do it in the Met Office with a £1 billion supercomputer, but it's part of the contract. They will have to make it net zero. So yes, the climate community and this community try to walk the talk and try to be as much possible conscious in terms of the net zero target. Yeah.
So just one last question. It will be to Cédric Buche. So I'm Jean-Marc Maurice from Business France. I'm in charge of the agrotech department. And so thank you for this really interesting presentation, and to see how robots can change human life. So my question is about all those simulation and mechanism of thinking to be close to the human thinking. So we see that in at this level for robots, competition, RoboCup. And my question is, what would be for CNRS Crossing Lab the vision, the long-term vision, and if you would like to apply this thinking method for different areas, for maybe agriculture, autonomous robotic, maybe for one of the projects of AFRAN is bushfire, maybe it can help bushfires, or defense, security, space. So, well, this is my question, Cedric. Thank you.
Thank you. Very nice question. So, in AI right now, you have two approaches. You have what we call machine learning from data. This is what most people are doing. It's quite efficient, but it's limited. In some cases, it's not working. You have another approaches, which is expert-based machine learning. So that means you have some human which can explain how it will work or to improve the systems. And I think the idea of crossing will be to engage both at the same time. So to merge data-driven approach with expert-driven information, we can be different. And using this collaboration between the human and the robot, or let's say the machine learning algorithm, we think we can improve the systems in all the fields that you mentioned, space, agriculture, and stuff like that. So yeah, we think it's a good idea, and we think both systems have advantages So machine learning is very good to extract some things that you don't even think about it, but it cannot find some obvious things. For example, we are here to talk about climate change and stuff like that. I can see that in like 1 second. Use a machine learning system to detect that in 1 second. It's impossible. But the machine learning technique can detect, okay, this guy is following the speech, this guy is sleeping very easily, and I cannot do it. So using both skills at the same time, merging humans and machine, we think we can improve the whole systems. Thank you.
Thank you very much. Please join with me in thanking our two speakers for this morning.